Properties of real numbers, and you should have seen these in algebra, but we're going to go back over them just to make sure. These are true for all real numbers. So that's every positive or negative whole number, that's every decimal, every fraction, and every variable, because we're in the real number system. So these are always going to be true, no matter what you're dealing with. The first one is the addition property of equality, and that one states that if I have two numbers, or a number and a variable, for example, or two expressions that are equal, I can add the same thing to both sides and they stay equal. Makes sense? If you have equal things and you add the same amount to them, they stay equal. Likewise, if I have two things that are already equal, I can subtract the same thing from both sides and it stays equal. Okay. And I can multiply both sides by the same thing and it stays equal. And I can divide both sides by the same thing and it stays equal. So these four properties are all essentially the same idea. I can add, subtract, multiply, or divide, and as long as I do it to both parts, everything will stay equal. This is what we use for solving equations. So you're very familiar with these even if you didn't know what to call them. Okay, so those are the operative properties, right? We perform operations, add, subtract, multiply, or divide. The next one on the list is called the reflexive property, and it's called reflexive because it's like a reflection. Okay? And what we have is the same thing on both sides. A equals A, 20 equals 20. X plus 4 equals X plus 4. As long as it's identical on both sides, it's perfect reflection. And in geometry, the reflexive property is usually used to introduce new things. When we're talking about a proof, we can't just bring some new angle or new line or new number into the proof. We have to introduce it. We have to give it a reason for being there, and so we use the reflexive property. We'll say like angle A equals angle A, and now it's been brought in and it's been introduced, and it's justified because it does equal itself. Okay. Symmetric property of equality is similar but not quite exactly the same. That's telling me if A is equal to B, then B is equal to A. And what this allows me to do is rearrange things around that equal sign. So I can take an equation and I can flip it around to make it more manageable. And this is the property that lets me do that. Because sometimes it might make more sense for it to look like this, and sometimes it might make more sense for it to look like that. And those are equivalent, so I can do that. I can flip it around. The transitive property is kind of like our law of syllogism. It says if A equals B and B equals C, then A equals C. And we have this thing in the middle that's happening, this B and B. That's kind of like our middleman. This is the transitive property because it's making a transition from A to B to C. Well, we can take B out. And that's when you recognize transitive, is when you see the same thing on both sides of the word and, like this. Take that chunk out and put the two ends together. That's transitive property. So this is the take out the middleman kind of thing. And then transitive property and substitution property get confused sometimes because they're very similar. Okay, the difference is with transitive property, you go from A to B and then B to C. So they match in the middle. With substitution, I'm saying A is the same as B and C is the same as B, and that allows me to substitute in for A and C. But if you look here, it's B and C, not B and B. So that's really, quite honestly, the only difference between substitution and transitive is the way it's arranged. Flip this around and you have transitive property. So these two can often be used for each other, and that's okay because they both essentially say the same thing. If you have two things that are equal to some third thing, then those two things are equal to each other. Okay. Distributive property tells me that if I have multiplication to a parenthesis, every item inside the parenthesis gets multiplied by that item on the outside. And that's good for addition or subtraction. An algebraic proof. These are proofs using a series of algebraic statements. Essentially, they outline how to solve an equation. And this will be the first step into formal proofs. And I'm going to use algebra because you guys have taken algebra, and so it should make a little bit more sense that way. So we're going to start with fixing this typo right here. Okay. So prove that if negative 5x plus 4 equals 70, then x equals negative 18. And then we're going to write a justification for each step. So at this point, we're still not going to do a formal proof, but I'm just going to take you kind of through the steps of solving the equation and justifying each part. So I'm going to write down the equation. And the reason we can write down the equation is because it was given to us. Okay. The next thing we do in solving an equation is we distribute that 5 . And in order to distribute that 5, I use the distributive property. Okay. Then, after I've distributed that 5, the next thing we would do would be to add 20 to both sides. So I get negative 5x is equal to 90, and the reason I did that was the addition property. Once I've done that, our next step is that we divide by negative 5. So x is equal to negative 18, and the way we were able to do that was by the division property. Except for division doesn't have that extra s in it. Once we make this into a formal proof, this row of the math that we've done becomes our statements. And this row of the reasons, well, there are reasons. We don't enter in to the formal proof, we don't put in our distribution lines, we don't put in our plus 20s, we don't put in our minus 5s, negative 5s that we're dividing by. We do this row, this row, this row, and this row because it's formal. So it's supposed to be very concise and clear and structured. State the properties that justify each step. So if I take, if 4 plus negative 5 equals negative 1, then x plus 4 plus negative 5 equals x minus 1. So we have between here and here, let's look at that real quickly. Between this part and this part, what has changed? We added an x, right?
So it's the substitution property.
Nope. What happened here to here? And the green? What changed? We added an x. We added the same thing to both sides. So this is addition property. Okay. When we look at if 5 equals y, then y equals 5. What changed between this part and this part? They were switched. And when we just flip things around the equal sign, that's the symmetric property. Okay. Let's do this one where we write the justifications for each step. So the first thing we do is we take the equation part and write that down. And the reason we can do that is because it's given. The next thing we would do to solve this equation is we would add 13 to both sides. So we get 2x is equal to 8, and that was using the addition property. And then the next thing we would do is we would divide both sides by 2, and we would get x equals 4, and that's because we used the division property. Okay, when you look at these, and you're trying to figure out which property it is, look at the difference between the if part and the then part. What changed? Okay. Anybody get these? In geometry, we most frequently use the two-column proof, which is the formal proof. Okay, and it contains 2 columns, 1 column for statements, and 1 column for reasons. When we create our 2-column proof, we typically draw a line, draw another line. This side is for statements, and this side is for reasons. Okay. And then you can either number them or not. You can put more lines in here for each statement or reason if you choose to. That's just formatting. But every statement has a corresponding reason. So we wouldn't leave any blank spots, right? So if I have a statement here, I won't leave a blank spot here. So our first statement will always be whatever was given. That's always going to be the very first thing you write in the proof is the given information. So we have been given C equals 5/9 F minus 32. Okay, and we're going to convert it to F equals 9/5 C plus 32. And in order to do that, we're going to go through the algebraic process of doing the steps to get from here to here. So the next thing we want to do is get rid of this 5/9. Okay.
So if you multiply 9 over 5.
Yeah. So I can say that 9 over 5 times C is equal to F minus 32. What I did is I used the multiplication property. And what you don't write into the proof is the part where you do this multiplication. That doesn't get written in. It's there, we did it, we just don't put it in there. So I've multiplied both sides by 9/5, sorry. And then I'm going to add 32 to both sides. Oops. And so for that one, I use the addition property. And see how I want it to be F is equal to 9/5 C plus 32? So I'm going to turn it around so that it's in the right format. And the thing that allows me to do that is the symmetric property.
Oh, is that reflective?
Now, reflexive is when it's the same exact identical thing on both sides. So it would be F equals F.
Okay.
There's not, it can't be, these two sides have to look like a reflection. They have to look exactly the same in order for it to be reflexive property. Symmetric property is just when you've rotated it around the equal sign. So you just switch places. Again, we start by making our two columns. We have statements and reasons. Okay. The if part is the given part. So this is given, and this is what we're trying to prove. Okay. The first thing I would do with, I'm trying to clear out to get to just x, is I'm going to get rid of this minus 8. So I'm going to add 8 to both sides. And again, though, I'm not writing that step in, but I've used the addition property. I'm writing that too far away. Hold on, I have to make that smaller. Okay. The next thing I need to do is get rid of that divided by 2. So I'm going to multiply both sides by 2. So I use the multiplication property. Then the next step in solving this would be to get rid of the 1. So I'm going to subtract it from both sides. So I have used subtraction property. Then I finally divide both sides by 5 using the division property to get to the statement I was trying to prove. So here's what we were trying to prove. Here's what we proved. We did it. For this version of the proof, we take our proof statement, our x equals 3, and we go ahead and plug that in using substitution. I took the 3 that I'm trying to prove that x equals 3. So if I put 3 in there, I'd still be proving it, right? So I used substitution. The minus 8 should still be there, sorry. It was 5x minus 1, yeah? Yeah, okay. So then 5 times 3 is 15 minus 1 divided by 2 minus 8 equals 0. 5 times 3 is 15. That's also substitution, because I've substituted the 15 for the 5 times 3.
So you have -1 -8.
Well, this is still a fraction, right?
It's +1.
Was it plus 1?
Yes.
Oh, it is plus 1. Okay, so I just copied it down wrong. Okay, so I have 16 divided by 2 minus 8 equals 0, substitution. 16 divided by 2 is 8 minus 8 equals 0, substitution. 0 equals 0, substitution. Or sorry, not sub, well, and then, actually that's reflexive. No, that's substitution. Then this symbol right here means therefore.
Therefore?
These 3 dots, that means therefore. That's reflexive. Because 0 equals 0, that was true, that's the reflexive property.
Does that always work? Your way?
Algebra. In algebra will work. If they give you what x equals, you could do it this way.
Really?
If they give you what, if they give you what x equals, but only on an algebraic proof will this work. So the reason I can say reflexive, even though this is not reflexive, this was. We use substitution to get from here to here. Then that is true of the reflexive property. So that tells me that that 3 I substituted in way back at the top was true. So that's why I say therefore x equals 3 based off of the reflexive property. So there's 2 ways you can get to this. You can either go through the solving and write down the steps of what you're doing as you go, or you can go and plug in the answer and make sure you get a true statement.
Okay.
But don't get confused, and so yes, I multiplied here, but that's not the multiplication property, because the multiplication property is if you multiply both sides of the equation. I didn't multiply both sides of the equation by something. What I did is I substituted in 15 for 5 times 3. So just be really careful with that. This is all going to be substitution on these, unless you then add or subtract something to both sides. Or if you do it to both sides is when it's addition or subtraction or those properties. Okay. Just for time, I'm going to go ahead and skip that. We have a proof for you guys to try here. What do we do to the next line? Yeah, they're, like I said, they're splitting it into 2 steps. So we add 5 to both sides. And then what happens when I actually do this and I get 1 plus 5 is 6 is substitution. silly proof. Then I divide both sides by 6 is division. And then they'll say x equals 1 is substitution. So basically, in order to make you use substitution, they are putting extra steps into this proof. You could do this proof in less steps. Given 6x minus 5 is equal to 1, subtraction. 6x is equal to 6, addition. And then x is equal to 1, division. So you could have a 4-step proof, or you could have this 7-step proof. These properties, remember I said that they work for all numbers and variables and fractions and decimals and everything. They also work for segments and angles as well. So if I have segments with a length, so AB equals CD, I can add the same length to both sides.
Oh, that means adding?
Yeah, this is this is when you don't have the line over top of it, it's referring to the length of the segment.
Okay, what if it says like it has the line over it?
Then it's segment addition property, not addition property. It's different, totally different. We'll get into that in the next thing. So if you have no line, it's talking about the length. So I can subtract the same length from both sides and it'll still be equal. Or I can multiply both of them by the same thing and it'll still be equal. Like if I double the length. Or if I divide the length by the same thing, for example, if I cut it in half. Okay. Now it doesn't have to be 2, it could be anything. If you multiply both sides by the same thing, it's still valid. If I have segments, it's equal to itself. I can, if AB, the length of AB is the same as CD, then the length of CD is the same as AB. I can reflect it or symmetric it around the equal sign. If AB is equal to CD and CD is equal to DE, then AB is equal to DE. Same idea, we have a middleman. And then substitution. If AB equals CD and DE equals CD, then AB equals DE. And it'll be the same with angles, and I'll go over that some more tomorrow. For tonight, on the homework, you're going to need to do page 26. Wait, sorry, page 25, number 7, and page 26, there's just the 2, so 1 and 2.